So let's recap the important aspects of what we discussed yesterday, right? So the essential difference that time-dependent perturbation theory offers that you have not seen thus far in your quantum mechanics course is that it allows the possibility of transitions between what were once stationary states, right? So you start with the Hamiltonian H0, right? And about whom you know everything, like you know how to diagonalize this Hamiltonian and get the energy eigenvalues and the eigenkets, right? And now, since I have nothing better to do, I will add to this Hamiltonian some piece that depends on time. And now I want to ask the question. Okay, before I actually do that, I know that I can now write any state psi as a linear combination of the eigenkets of this Hamiltonian, because after all, the Hamiltonian is a unitary, as a Hermitian operator. So I can always express any state as the eigenkets of a Hermitian operator. And if I want to know how this particular state that I have written down psi evolves in time, the answer is quite easy, because I know how all the stationary states evolve in time. I just need to tag on the time dependence, right? So psi of t would simply be equal to Cn e to the minus I n0 t over h bar n0, right? So now if I make my Hamiltonian time dependent by fiat like this, okay, then we discussed yesterday that the difference is that I can again express any state as a linear combination of the eigenkets of the original Hamiltonian, because the original Hamiltonian is still a Hermitian operator, and it still furnishes eigenkets that are orthonormal. However, if I want to calculate the time dependence of these states, it won't be a simple matter of just tagging on the exponentials, because as I turn on the time dependence, these n zeros won't be the stationary states of the new Hamiltonian anymore. So I cannot simply conclude that time independence is just this e to the minus IET over h bar. So the way we progressed is without actually solving the Schrodinger equation with this new Hamiltonian, we wrote this time dependence as some other factor tagged on along with the exponentials. Okay. And then we claimed that the whole point of perturbation theory, or the whole point of this entire problem, is to figure out what these dn of t's are, and we're going to do it in perturbation theory. And we developed a systematic formula to help us understand what these dn of t's are, and we figured out that these d's obey a formula which we wrote down as dnt. What was that? E to the I omega m n t, the matrix element of the perturbation between the unperturbed states. Okay, so this is where we stopped yesterday. So what is essentially happening, the physics here is that if I don't turn on the h tilde, and if I start with a particular state, which is some particular linear combination of n zeros like this, that state will remain in that particular linear combination of n zeros with the time dependence added along. But if I turn on a time dependence, it is possible that a state that starts out with some when h tilde is turned on, excuse me, a state that starts out in a particular, for example, eigenket of h0, say m0, n0, can later evolve into a different state, say m0. Okay, this is the essential difference. This is the stuff that doesn't happen if I don't turn on the h tilde. So the goal of
So what do you mean by turning on the perturbed Hamiltonian?
So typically the way so this is exactly what we did in the time independent perturbation theory also, right? So we started out with the Hamiltonian H, which is just H0, and then we added on some small perturbation H tilde, and we controlled it with some parameter lambda, right? And there, since the H tilde was also time independent, we never bothered about when it was turned on and when it was turned off, right? Because it is time independent Hamiltonian, I can assume that this is always there. But of course, I can still assume that the parameter that helps me switch this H tilde on and off, which is lambda parameter. For example, if I have a knob where I adjust lambda from 0 to 1, if I push the knob to 0, of course, I don't have any perturbation. If I push the knob to crank up to 1, for example, I have maximum perturbation and so on and so forth. So this is how you understand the time independent perturbation theory part. In the time dependent perturbation theory, typically what happens is that you assume a certain time at which this H tilde is turned on and certain time at which H tilde is turned off. And it is completely up to you and the problem. For example, how long you want this H tilde to act. For example, I can turn on this H tilde at t equals minus infinity and turn it off at t equals plus infinity, which is another way of saying that H tilde is always there in some sense. Or I can turn on the H tilde at t equal to 0 and turn it off at t equal to 10 seconds. It's completely up to me, in which case all these transitions will only happen in that particular time window, right? And after 10 seconds, of course, my Hamiltonian is again H0, so the system will again be easily solved, and so on and so forth. So turning on and off the Hamiltonian simply means that since it is a time dependent process, you also have to decide when you turn on the perturbation. For example, if this is an external electromagnetic pulse that you're sending, you decide when you start shooting the pulses into the hydrogen atom and when you stop. Okay? Makes sense?
Yes, sir. But does that mean like for a particular time interval, Hamiltonian is perturbed, and for some time it is not?
It is possible. So it depends on the kind of perturbation and the length for which the perturbation acts. Again, as I said, it is possible that the perturbation is always there. There is certainly a case we will actually solve a problem like that. Or it is also possible that the perturbation only acts for a finite time. Okay?
Okay, sir. Okay.
It's you who are perturbing the system, so it's in your control. Okay? So,
Okay, sir.
so we wrote down this formula that determines the rate of transition. So for example, what is the rate at which the state n0, the initial state, becomes a different eigenstate of the original Hamiltonian? Okay, so only because this H tilde is making curious things happen. And this formula helps us figure out the rate. So remember that, so again, so if you look at this formula for psi of t, why is the dn of t important? Well, if I want to calculate the amplitude for this psi of t to be along an m0 direction, then that particular probability for this state to evolve into m0 is basically, I'll have to calculate this guy, right? Psi of t. And this is equal to dn of t e to the minus.
Sir, it is not showing, I think.
Oh, I'm sorry. Okay. So if you want to calculate the probability that this psi of t can evolve into some other state m0 after some time, then I'll simply have to calculate the overlap of m0 with psi of t at that particular time, right? And this is this, but m0 and n0 are still orthonormal states. So this is delta mn. So this basically tells me this is dn of t e to the, oops, excuse me, dm of t e to the minus e m0t over h bar. And the probability that this can happen, that the state that starts out in some linear combination can end up in the state m0, is basically mod. Okay. And as you can guess, this is a time dependent process. which is why these amplitudes are also time dependent. So after like 10 seconds, the probability could be a completely different value. Okay, so this is why calculating this dm is important, because the absolute square of this dm tells me the probability for these transitions to occur. Okay, so let's again go back to that formula. So I'll introduce a slight change in notation. Okay, so typically one employs the notation that an initial state, what is the probability for an initial state to go into a particular final state? So M I will call F. Okay, so change in notation. I am interested in calculating rates of transition from an initial state, which I will call I0, to a final state, which I will call F0. So this initial state and final state, we have to properly define. This final state, of course, is some particular eigenstate of the original H0. And this initial state could be either a particular state of the particular eigenket of the original Hamiltonian H0 or some linear combination. Okay, so basically what I'm saying is that whenever I say M0, I'm going to now call it F0. But this I0 I have to define carefully. What do I mean by I0? I mean that since I wrote psi of t as dn e to the minus e n0 t over h bar n0, okay, basically my I0 initial state is what I call psi of 0. Okay, so psi of 0 is just a convenient way. For example, if my system starts out at time 5 seconds, for example, and if that is my initial time, I'll always time translate and claim that I'm starting at time t equal to 0. Okay. So this psi of 0 is what I call I0. This is equal to dn0. This becomes just 1 n0. Okay, which means my coefficients dn at time t equal to 0 are given by the overlap of that particular state n with, excuse me, I0. Okay, and this is nothing but delta ni. I might have as well called this sum over m dmt e to the minus iem, whatever. In that case, dm of 0 would be the overlap of m0 with I0, would be delta mi. Okay.
Sir, can you please repeat this step again?
Which step?
Sir, how we are getting dn0?
Okay. So you understand this step, psi of t, and I put t equal to 0 in this equation to get this equation. Is this the equation?
Yes, sir.
Okay.
Yes, sir.
So now if I have to get dn0, I will simply calculate. So remember how you calculate the coefficients in general, right? See, I0 and N0 are eigenkets of the original Hamiltonian H0, right? So I0 and N0 are in some sense the eigengets of the unperturbed Hamiltonian. So if I want to get the coefficient N0, I simply take the overlap. So I have this equation dn0 n0, okay, and now I take the overlap with on both sides with n. So I take the dot product. So this is equal to, or better still, take the dot product with a different vector. Okay, so it is obvious to you. M0 I0, right? What is this? This is basically delta mi. And what is the right hand side? The right hand side is dn0 m0 n0. Agreed?
Yes, sir.
And what is this? This is delta mn, right?
Yes, sir.
Out of this entire sum, there is only one term that survives, and that term is one for which n equals n, right?
Yes,
So
sir.
this tells you that dm of 0, which is nothing but m0 I0, is delta mi. Okay. Make sense?
Okay, sir. Yes, sir. Yes.
Okay. So now I need to set up this equation as a perturbation theory and calculate D term by term in perturbation theory. Well, so I will write this equation again, df dot of t, because I'm calling m as the final state. Now this is equal to n dnt. Well, here I cannot do anything because it's a sum over n e to the minus, oops, excuse me, e to the minus I, what was that? Omega fn, fnt, and then the matrix element f0 h tilde n0. Okay, so this is my master equation, and now I have to look at this equation order by order in perturbation theory. Okay, so the easiest thing to do would be just to calculate to 0th order. Now, what do I mean by I'm going to do this in perturbation theory? I'm going to assume that this D can be written as a 0th order value plus a first order value plus a second order value, and so on and so forth, right? So if I want to calculate D to 0th order, on the left hand side, I will have 0th order. But what is the right hand side? Is there a 0th order term on the right hand side? Well, I can write down the 0th order of Dn on the right hand side, but this matrix element is manifestly first order in the perturbation, right? There is manifestly a factor of h tilde on the right hand side. So there is no 0th order term on the right hand side. 0th order means 0th order in the perturbation, h tilde. So there is nothing that is order 0 on the right hand side, which means that if I want to calculate the 0th order transition rate, I will simply have the equation df0 dot of t is simply equal to 0. Okay. So if this notation confuses you, use the same notation that you studied in time independent perturbation theory, where we wrote everything in terms of some parameter lambda, right? So you write dn as lambda times dn, lambda 0 times dn0 plus lambda times dn1 plus lambda square times dn2, and so on and so forth. And you just equate the powers of lambda on both sides. And whatever you do, you'll find that to 0th order, there is no transition possible. Okay, df dot is 0, which means this is to 0th order, df0, excuse me, is just a constant. It doesn't change with time at all. So I might as well take this to be the value at time t equal to 0. But the value at time t equal to 0 is basically, we have figured it out here, dm of 0 is delta mi. So df of 0 should be just delta fi. And this makes sense. This simply says that to 0th order, when you don't have a perturbation at all, your initial state doesn't have any chance to evolve into anything new. So it will just stay. The final state will be the same as the initial state. That is what this is. So the magic happens starting the first order. So what is the first order correction? So to calculate this boxed equation to first order, remember that I should consistently keep things to first order. Now, on the right hand side, it is very simple. I only have one term. So I'll calculate df dot to the first order correction to df dot. But how should I treat the right hand side? Well, the right hand side has two terms, right? The d and the matrix element of the perturbation. The matrix element of the perturbation is already first order. So if I write d on the right hand side as a combination of 0th order, first order, and second order terms, I will find that the first order contribution on the right hand side is basically the multiplication of the 0th order term here times the first order term, which is the matrix element. Is this step clear? I'll pause and ask if there is any questions. Please look at this carefully and tell me if this is clear. Again, if you want to write in terms of lambdas, all I'm claiming is that if I write dn of t as some lambda 0, dn0 plus lambda dn1 and so on and so forth, the first order term on the right hand side is basically dn0 times the matrix element of the perturbation, because this term is already of order lambda. Okay, so that is what I am writing. There is no zeroth order term on the right hand side, and there is precisely one first order term on the right hand side. Similarly, if I calculate the second order term, then I will have two terms on the right hand side. One which is first order in dn times its matrix element. Sorry, I'll still have only one term. Okay, first order term in dn times the matrix element. If I want to calculate the third order correction on the right hand side, then I will have the second order dn here times the perturbation, so on and so forth. Okay. So this is the only possibility for the first order term, but dn0 we have already figured out is basically delta ni e to the I omega f n t f0 h tilde n0, right? And this delta function among all these states picks out that particular n for which n is equal to the initial state I. So this I can write as e to the I omega f I t times the matrix element of the perturbation between the initial and final states. Okay. So the first order correction can be written as minus I over h bar e to the I omega f I t f0 h tilde I0. Okay. So to first order, one can write the zeroth order plus the first order dft is equal to the zeroth order term plus the first order term, which implies that this is equal to delta fi minus I over h bar, sorry, df dot of t. Yes, minus I over h bar e to the I f0 h tilde I0. Okay, and this is trivially solved. If I integrate this equation, I get dft, which is basically, if I assume that my integration, my Hamiltonian is turned on at time t equal to 0, then my lower limit would be 0. If it's turned on at time t equal to minus infinity, the lower limit will be minus infinity. That depends on the problem at hand. E to the I omega f I t f0 h tilde I0 dt. Okay. So if you're confused about the same t appear here and there, then use a dummy variable here. So that's always a good idea. So put a t prime here, t prime dt prime. Okay. So as a practical matter, in time dependent perturbation theory, this is the first order. This is the most important formula. At first order, the rate of transition is given by the absolute square of this integration. Okay. Again, as I emphasized in the last lecture, this is one way of motivating this formula, but you can quickly understand that this will be a little unwieldy because of all these integrations and stuff like that. If I want to calculate the second order, I'll have to substitute the first order term in the mastered equation, where this one, the boxed equation, right? And then I should calculate the second order term and so on and so forth. But there is a better way to organize this perturbation theory in time dependent perturbation. And that is something I will explain to you in the next lecture. Okay, there is actually an elegant formalism based on what is called the interaction picture. I'm not doing that. I'm simply following the exact same kind of prescription that one employed in time independent perturbation theory and solving. Okay. So basically, this is what you would need to find. So let us actually do one example problem from your textbook, which I found was quite instructive. So the
Sir,
problem, yes.
sir, as you have mentioned, like it can be possible, like for a time interval, for there is no perturbation, like lambda equals to zero kind of thing. But we are doing integral here, and like if there is for a time interval delta t prime, and if there is no perturbation, so then the first order correction that we are doing, that would that be equal to zero, or still it would be equal to this integral?
So you are saying that if you turn on the perturbation only for a finite amount of time.
Yes, sir. Yes.
Yeah. So see, whatever the time. So let us say that you turn on the perturbation from t equal to minus 10 seconds to 10 seconds. Then the limits of this integration be minus 10 to plus 10. See,
Okay, it shouldn't be equal for the initial time. It shouldn't be equal to. It's not necessary to take limit from zero, right?
no. It depends on the problem at hand. I'm just taking zero because it is the most general. But in this problem that we will do a different time. In just 1 second. So again, so this way of motivating the formula is just one way of doing it. Again, so this is stop. So there is a much better way of motivating the formula that I will talk about in the next lecture. There, these questions will not appear because it will be obvious. Sorry, just give me 1 second. Okay. So to continue that point, so this is the example problem. Example. There is a one-dimensional simple harmonic oscillator. Okay, so obviously you know that H0 is basically P square over 2m plus 1/2 m omega square x square, right? And then this has stationary states n0, and you know that the eigenenergies are n plus 1/2 h bar omega. These are all things that you already know. Now suppose, now remember in the time independent perturbation theory, we added an h tilde, which was, we put this Hamiltonian, we put this simple harmonic oscillator, we assumed that it was charged and put it in an electric field, right? So it was something like this, if you guys remember this, right? But now we're going to take the same kind of perturbation, and if you guys remember, if you have this perturbation, for example, we found that energy levels just shift by a constant amount. But suppose if you tag on some kind of a time dependence minus t square over tau square, then it is possible that if you start out the simple harmonic oscillator at time t equal to 0, suppose if you start it out at some state, let us say the fifth excited state, then at some other finite state, the system can evolve to a different excited state, like the third state or the seventh state, whatever it is. Okay, so this is a problem that asks you to calculate the rate of transition for a particular case. So the problem states that the system is in the eigenstate, is in the state, initial state equals the ground state of the one-dimensional harmonic oscillator at time t equal to minus infinity. So not 0, but t equals minus infinity. And from t equals minus infinity to plus infinity, h tilde of t acts on the system. Okay. So, and suppose if you again make a measurement at t equal to plus infinity, what is the probability that the system evolves to a different state, some other state n0, where n is not n0 is not equal to 0, right? I'm not interested in the case where the system does not change at all. So I don't want n0 to be the ground state. I want the ground state at time t equal to minus infinity to evolve to a different state at t equal to plus infinity. Okay, so I'm giving enough time for the system to evolve, and I'm asking what is the probability that the system will evolve to a new eigenstate of the original unperturbed harmonic oscillator Hamiltonian at time t equal to plus infinity. Is the statement of the problem clear? This is a problem from Shankar's textbook. Okay, so basically I'll have to calculate the probability. So probability for the zero state to evolve to a different state n is at time t equal to infinity is this guy. So I'll have to simply calculate d at time t equal to plus infinity and take the absolute mod of that particular number. So the way I will calculate dn is simply I will use this formula that we have derived. This is minus I over h bar. In this case, the perturbation acts from minus infinity to plus infinity, right? And then e to the I omega fi. So I'll omega fi. I'll use a different t here, or I'll use the same t here. I think it should be obvious. Okay, and then the Hamiltonian is itself minus EEX minus EE. Okay, remember that I want the Hamiltonian sandwich between the initial states and the final states. The initial state, of course, is the ground state. The final state is some n0. Tt. Okay, is this clear? So this part is basically f0 h tilde of t n0, right? Of course, I forgot the e to the minus t square over tau square part. Okay. So this is just plugging in, taking this formula and plugging in the Hamiltonian here. So what is f? F is the nth state. So omega fi is 1 over h bar ef minus ei. This is 1 over h bar. Ef is the energy of the nth state, whatever that state is, I do not know. This is n plus 1/2 h bar omega. Okay. Minus ei is the energy of the ground state, because the initial state is the ground state of the simple harmonic oscillator. So this is 1/2 h bar omega. Oops. So this is basically n omega. So dn of infinity, where I'm calculating the probability amplitude for the simple harmonic oscillator to evolve under this time dependent perturbation theory into a different state n, starting out with the state n0, would be take out all these constants outside, minus infinity to plus infinity, e to the I n omega t e to the minus t square over tau square times n0 x0 dt. So far so good. Any questions about this? Any questions, any comments? Okay, so the remaining is basic simple harmonic oscillator stuff that you guys know already. I will write x as square root of h bar over 2m omega times a plus a dagger. And you guys know that a acting on 0 is just 0, and a dagger acting on 0 gives me the first excited state. So n0 x0 would be square root of h bar over 2m omega times n a plus a dagger 0, which is equal to a acting on 0 is 0, a dagger acting on 0 is 1. So this is the overlap of n and 1. So this is basically h bar over 2m omega delta n1. So what does this mean? This means that under this particular perturbation, the matrix element can only be non-zero if the final state is the first excited state. So this means that under this particular kind of perturbation, the x-dependent perturbation, the simple harmonic oscillator that starts out in the ground state can at most go to the first excited state. It is not possible for it to go to any other state under this perturbation. Okay, so it means my d n infinity is just the amplitude for it to go to the first excited state. There is only one possibility here. This is equal to, put in all factors of I and E and finish this yourself, I E over h bar times square root of h bar over 2m omega. Okay, n is 1, so this is minus infinity to infinity, e to the I omega t, e to the minus t square over tau square dt. Okay, so what remains is basically just do out this integration, but this integration, you can actually combine these two terms and write it as an absolute square, and this is just the integration of a Gaussian. That is why the limits are given as minus infinity to plus infinity. So this is just a Gaussian. So whatever you do, d1 infinity would be proportional to something like e to the minus, what would it be? Minus omega square tau square over 4. Okay, you'll have to figure out what the proportionality constant is yourself by doing out this integration. In other words, the probability for the state to go from 0 to 1 is basically, so let us say that this is equal to some k times e to the minus omega square tau square over 4, then k square mod k square e to the minus omega square tau square over 2. Okay, so please calculate k yourself, or you can just look up Shankar's book and the answer is given over there. So practically speaking, this is how you solve problems in time-dependent perturbation theory stuff. You typically start out with the unperturbed Hamiltonian. Okay, you turn on the perturbation and then you ask the question, what is the possibility that a state that starts out in some linear combination of the unperturbed states finally evolves to a different linear combination of the unperturbed states? A fact that is just not possible if you don't have time-dependent Hamiltonians. Okay. So I will stop here for today actually, because I need to systematically develop a procedure for developing understanding the perturbation series in this particular example, time-dependent perturbation theory. So I'll have to introduce what is called the interaction picture, which will take a little bit of time, so I don't have enough time. So I'll stop here for today, and I will motivate this exact same perturbation theory from a different angle next week. Okay, so where we will talk about a new picture of the new picture of quantum mechanics called the interaction picture, in addition to the Schrodinger and Heisenberg pictures, and we will actually understand how this interaction picture helps us to understand this time-dependent perturbation theory processes in a much simpler and a very elegant diagrammatic fashion. Okay, so this will be reminiscent of what are called Feynman diagrams later, but it's not quite the same thing. But you will still be able to understand the whole perturbation series as a series of diagrams with insertions of the interaction Hamiltonian here and there. So it will be actually intuitively a little bit more clear how this whole thing plays out. Okay, so we will develop this formalism next week.